Okay, we're going to do some flow rate talks today. We're going to do a little bit on the printer with trying to estimate our flow rate, or at least when it's maximized, and we'll be able to get close with that. But I don't have the scale I need. The scale that I have here is not going to work quite the way we need it to. So we'll go through the process. We're going to do that. We'll talk about flow rate, talk about some other things. Let's just jump into it. Flow rate, we've done the little box. I was looking around for one. I don't see one. We've done the little box where it's a hollow box, kind of like the calibration cube, and you measure the thickness of the walls to figure out if you're flowing enough material out of the nozzle to generate the thickness of wall that you expect to have. Like if you have a 0.4 millimeter nozzle and you're trying to make a 0.4 millimeter line width, did you actually get that 0.4 millimeters coming out of the nozzle? And so that's kind of where we started with flow rate it's been a month or so when we did that. What we're talking about now is more like the flow rate, like what is the maximum we can get. So our printer over here, let's go look at our printer. Well, that's not our printer, that's the flow rate test I did. There it is, let's see if we can make it, there we go. There's our printer. So we changed out to one of the micro Swiss direct drives, and we have a 0.6 millimeter nozzle in there. Let's get this out of the way. And so we're trying to get, as much filament flow out of the nozzle as we can with the direct drive and the larger diameter nozzle. The direct drive doesn't necessarily influence the flow rate as far as making it more, but it's more controllable. We could probably get a similar amount of flow rate in a Bowden tube printer. That would be interesting to try and see. Does the direct drive max out at a higher flow rate than a Bowden tube? Because it might. I don't know. I haven't actually tested that before. Anyway, we've made all these changes, and what you see on the print bed, these are the remnants of the little first flow rate test that I did do. That's the purge line. The actual objects are down here. So each one of these is supposed to be a certain amount of material requested to flow through the nozzle at different temperatures. So I did 3 different temperatures and at different flow rates. Now these are a little bit too small. This is all 100 millimeters of filament. So if you ran 100 millimeters of filament through the extruder, then you get this amount of filament coming out. And so the idea would be that you could go in and track where did the filament not all come out of the nozzle. You weren't able to deliver it all at some of the higher flow rates or maybe a lower temperature. This little set is a little, my scale, you can kind of see the edge of it over here. This scale only measures in grams. It doesn't measure in fractions of grams. And so these don't even weigh 1 gram. So I would either need to print larger samples here, which we could do, it just take longer. So instead of extruding 100 millimeters of filament, maybe we extrude 300 millimeters or 400 millimeters. So it's a lot more filament. I didn't want to do that, so what I did is I just ordered a scale that's going to go down to hundreds of grams, and we'll go from there. That just won't be here right now. So why do I even want to know all of this stuff? So normal printing, if you're just throwing something in Cura or Prusa slicer or whatever your slicer is and letting it print, then you're probably not concerned with flow rate. You can actually see the flow rate in Cura. Let's go to Cura. And let's see, there's Prusa, where's Cura? There's Cura. This is this is a miniature version of the hood scoop we did last time. So I just dropped it into here. Actually, I wouldn't print it this way. It looks like here's the front of the printer. If you're ever printing something tall and skinny, it's best on a bed slinger printer. It's best to orient it more like that if you're going to print it on its end. Because the bed's moving. Oh, hold up. You're not looking at the. Let's fix that. No, that's not it. Oh, whoops. I'm on the wrong thing. There we go. Now you're looking at Cura. So all I said is that this, so this little piece was in here like this, or something like that. And I said that whenever you're printing a tall, skinny piece on a bed slinger, where this bed moves back and forth to create the y-axis, then it's better to align your tall, skinny print with that motion. Otherwise, if it's perpendicular to that, as the bed moves back and forth, this gets taller and taller as you print it. The top is going to be very wobbly, and you're going to get a very uneven surface finish. You'll get better results if you align that so that as the bed moves back and forth, it doesn't wobble the print nearly as bad. I would probably actually tilt this, maybe, something like that, probably, if I were actually going to print it. This is way too small. This is obviously, like 2 inches tall or whatever. Anyway, that's not the point. The point is, we were talking about flow rate. So we do have some settings here. If I type flow in, now you can see this is a percentage here. All of these are percentages, these 95s, and there's a couple of hundreds down here. This is based on that little box test. So we did the box test, and we find out that our walls are printing way thicker. This has got a 0.6 millimeter nozzle in it, and we're getting 0.63, thicker walls than what we expected to get. So we dropped down the flow rate here to some percentage, 95% of what the calculated flow rate should be, to try and smooth out our surface finish. So it doesn't say anywhere here what the flow rate is, though. But if you slice it, so if we slice our model, I guess it's probably taking longer to slice. I don't even know what my settings are, so that's not really important. But if I go here, and in my color scheme, normally this is on line type, right? So you see something like this, and it's showing these are all shells because it's so thin. So there's nothing there to actually print. But if you select flow, what it shows you is the flow rate. So you can see down here towards the bottom, it's having to flow nearly 3. This units are cubic millimeters per second. So that's how many cubic millimeters are coming out of the nozzle every second. And so you can see as it gets higher up here, it is requiring less flow rate. So I would need to make sure that my printer is able to deliver 2.85 cubic millimeters of filament per second. Otherwise, I'm going to have gaps in the model. Prusa does this a little bit differently. Let's go to Prusa. So let's put the same model in there. I think it's that one. Okay, that's fine. So it came out really tiny. Let's scale it up a little bit. Let's go to, it might be a millimeter. Yeah, that looks about the same there. All right, again, I would rotate it around to align it with the direction of motion there. And I'd probably tilt it over. Maybe 40, I don't know if let's do 35 degrees. And then slice it up. I don't know what our settings are here either. This one must have support turned off on this one. So Prusa Slicer, what it does is you have settings that I didn't even go into any of them here. So let's go to the print settings tab, and in speed, so there's a whole bunch of print settings here. Speed, down here, let's make sure, yeah, it's on the screen. I don't know if I can make those any larger though. There's this max volumetric speed. Now mine is set to 0 here, but what Prusa Slicer does is it says that tell me what your maximum is. If you put in 0, then it's no maximum. But tell me what your printer is capable of doing as far as delivering filament. So what is it? Is it 7 millimeters cubed per second? What is it? And I will make sure that I never try to deliver more than that filament. So it kind of comes at it from more of a, hey, I know what my maximum flow rate is, and I want to slice with not exceeding that. So I won't ever get any of the gaps in my model due to insufficient flow. So mine's set to 0 on the printer. I guess I should set it back to 0. But in the filament, so each filament might have a different flow rate that your printer is able to deal with on that filament. Maybe it melts at higher temperatures, or it's just a more abrasive filament, and whatever reasons. But the filament settings, if you go to advanced, I think it's in advanced. Yeah, right there. You can set per filament. So this is the generic PLA Neo. And whatever filament you've defined in here, these are all the basic. Actually, there's a Voron one I put in, but all these others are the basic ones that come with Prusa. You can set a maximum volumetric speed per filament. So it looks like this one's set to 12 cubic millimeters per second. So I would need to make sure that my printer can deliver 12 millimeters cubed per second of filament. And that's where the little test kind of comes in. So let's go through how to create the test so you can figure out, well, what can I deliver? You know, you could just try and measure it, but there's a little bit cleaner way to do it. Let's close up Prusa Slicer. We don't need that, and we don't really need Cura. I'm not going to print this thing, at least not at that scale. So if we go to our flow rate here, I've got a couple of different references. Some of these are journal. Actually, that one's a journal article. But this GitHub page and this web page are from Stefan at CNC Kitchen, where he developed a tool that you can use to do this kind of flow rate testing a little easier, so you don't have to code it yourself. The GitHub page is actually going to take us over to the file itself, but in there there's a web-based tool. So I fall uphill, whoever that is, took Stefan's Excel-based, or well, was it Excel-based? I don't know. I think it was Excel-based, and then maybe a Python conversion to write the G code. I'm not sure what he did. I guess we could look at it and see. It was Visual Basic, so it's Excel and Visual Basic took. That's probably what wrote the actual G code. But anyway, they took that and put it over here on this web page. So we can go to the web page. So what will happen here, you get a little preview of, well, let's zoom in on that. Get a little preview of what you're trying to print. So you can see the little purge lines, and then the these little lines here are showing where the filament is going to come out. And you set up your printer. So a little Ender 3 is 225 by 225, or maybe you have a bigger printer, or you don't want to print all the way at the edge of your printer. The bed margin is basically how far to indent before printing anything. Yeah, you can kind of see that on my, if we look over here. Well, not there though. Look over there. There's a 10 millimeter indentation from the edge. Now there's not one from the front. I'm not sure why it didn't indent 10 millimeters from the front also. Do you want to print at the front of the bed first or the back of the bed first? I did front to back. What is your filament diameter? So these are the two most common filament diameters, and if you had something different, like you were actually measuring your filament diameter and it was something other than 1.75, you can't really, I don't think you can put that in here. You just have a drop down, so you'd have to go and modify the G code or go use the Excel thing that Stefan has. Here we only have these two options. I'm using that Prusa Mint Galaxy Purple because it's pretty consistent diameter, so I don't have the filament change in diameter on me, and it is 1.75 millimeters. Travel speed, how far when you're not printing, how fast do you want to move? 100's fine for that. What's your normal bed temperature? I didn't get in the bed, the PEO sheet from last time, but I did put, remember we put a magnetic sheet on there, and I did put one of the textured beds that I have. I don't remember even where this one came from. This one might be an energetic, but I don't remember. But it's just a PEI sheet, flex, you know, it's a magnetic sheet. So I did put that on there. So we're printing on that. And I've got the bed set at 60 for that. That seems to work fine. Fan speed, if you need to cool the material. So I'm printing PLA, so I'm going to run the fan at 100%. Retraction settings, I just went to Cura and took the retraction settings that I've been using and used those. So a millimeter, since I could probably get away with a little less than that, but on the direct drive, but a millimeter seems to be working okay. Direct drives, you usually don't want much more than a millimeter of retraction. The Bowden tubes, you might be at 5 to 10 millimeters. I've got a slow-ish retraction speed. You want to do as little retraction as slow as you can, and still not have strings. And these settings seem to work for this setup. If you're going the base Ender 3, it's probably more like 8 and 40 or so. Here's generating the pattern. So how much space do you want between the test? This sort of has to do with the size of your print head. Mine's off the screen right now. So, how much space do you need between here? What I did is I just let it print, and then I don't see them now, but I had some tweezers and I just grabbed the parts off of the bed, because if they stay on the bed, this could knock them over, and then you get them all confused, and you don't know which flow test went with which speed and temperature. So I used tweezers, grabbed them off of here, and put them in a grid over here to make sure that I didn't lose track of which ones were which. And then I made little notes. So during this one, this is printed at 200 Celsius, trying to extrude 17 millimeters per millimeters cubed per second. And it was skipping. So I could hear the extruder trying to deliver filament, but it just couldn't. It was skipping. And so I know that I've definitely reached the max at 17. I can't print 17 millimeters per millimeters cubed per second, at least not at 200. It was fine when I was at 215 or even 230. But at the 230 and the lower extrusion rate, there was a lot of popping. So I was over melting the filament. And so it didn't come out as good. So this one and this one, I can just tell without even measuring their sizes that those are kind of my bounds on where I can print. All the others seem reasonably good. I need to get the finer resolution scale in to make sure that all of these are not dropping off on how much filament they're actually delivering. But this one is too hot with too low of a temperature. Now, or not too low of a temperature, too low of a flow rate. When I was doing higher flow rates, this was fine. And this one was too cold for trying to deliver as much filament as I was trying to deliver. So I'd have to stay somewhere in this zone for it to work better. You can't always control minimum flow rate. I don't know of a way to force your printer to always print at least at a certain flow rate. I'll have to investigate if there's some way to do that. I don't think that I know of one. You can just keep increasing your print speed, though, and it will try to deliver faster, flow rates. But I don't think you have control over what that number is. What is your minimum flow rate? I don't know of any way you can actually control that, other than you can manipulate it by faster print speeds. All right, let's go back to our G-code generator. So there's the X spacing. So this was the Y. How many? So this 50 is, just so we'll just keep flipping back and forth. The 50 is this spacing. The 50 is this spacing between the different flow rates. So this was 8 millimeters cubed per second, 11, 14, 17. Looks like I could have probably fit another one in there. And the 38, the next one, is this spacing. Well, it's actually this spacing. This guy would have been right there. And so 38 is that spacing. Okay. Dwell time, so 20. That's just how long does it sit there on letting the filament dry before it tries to move on. I did have a little bit of issue with it wanting to pull the little filament blobs away. So that's another reason I sat and I grabbed them off of the printer with tweezers. They are hot, so don't grab them with your hands. But grab them with tweezers so that they didn't get drug around all over the print. There's the starting flow rate. So that was 8 for me, millimeters cubed per second. And then how much do you want to increment each row? So I did 3. And then how many rows? It looks like I probably could have done 5. That 5th one would have been way at the back there, but I think there was room for it. I think we'd have to try it and see. So I could have gotten up to 20 millimeters cubed per second. That's a relatively high flow rate. Probably too much for the 200 degree for sure, because the 17 was too much. So your start temperature, what do you normally think you print at? So for PLA, I'm printing at least at 200, although you can usually print a little lower. But generally, that's going to be not as good on the layer adhesion. So I usually do 200 at least. And then what you want to go up by. So I did only have room for 3 temperatures. If I wanted to do another set of temperatures, I'd have to do another batch of prints. They just didn't fit on the bed. I went up by 15s. When I'm actually printing, I go up by 5s. But that would only give me 200, 205, and 210. Then I'd have to do another set, 215, 220, 225, which that would be okay. That tells me what the end temperature is going to be. Where does the Z need to be when you go to park so that it doesn't crash into anything? I'd probably actually raise that up maybe to 20 now that I've seen it do it a couple of times. This is just in the G code. I didn't bother looking at that. I did not change any of the start or end G code. It worked fine the way it was. Prime line length. So the prime line is, oh, wrong button. How long is this little purge line? 25 millimeters seemed fine. The prime amount is how much filament did you request to be delivered during that purge. You're not measuring these, so all you want is make sure the filament, the nozzle is clear. So these 25 and 20 worked fine. The speed, prime speed, is how fast did it print this line. The wipe length is, put this guy back up here, is this distance here. How far is between the purge line and your blob. The blob height, I did 10. The first time I did, I was extruding 200 millimeters of filament and did 10, and that wasn't tall enough. It was gumming up on the nozzle. So if I did 200 millimeters of filament coming out, I would probably go to at least a height of 15 here. And then extrusion amount is how much filament are you trying to extrude. So that goes through these. So to make it faster and to not have it gum up on the nozzle, I only extruded 100 millimeters of filament. The downside of that is now I need a finer scale to actually measure that, because all of these pieces that I printed weigh less than 1 gram, and my scale's minimum was 1 gram, minimum resolution. So we'll see once I get a better scale on hand. And then what you do is you give it a file name and you download the G code, and you just take, I'm using Clipper over here, so I had to go over to here, there's the 2 different G codes that I used. The first one was the 200 millimeters of extruded filament. I canceled that one because it wouldn't let go of the blob off of the nozzle. So that the one that you see the little blobs from, or this one. And I did have to do one thing. I don't think you would have to do this on just your Ender 3, but if you're running Clipper, then I did have to go in and change or add a line, actually. So let's see, let's go to the printer configuration. Where is that at? In here. So I had to add this line You see that? It's kind of small. I don't know if I can make it, can't make it larger. But what it says is max underscore extrude underscore cross section underscore cross underscore section. So max extrude cross section. I had to change that to 50. 50 is way too large. But it was trying to request too much filament cross-sectional area coming out of the nozzle than what Clipper had built in. I think Clipper had 1.44 millimeters squared built in, and it was requesting 1.92 or something like that. I guess it says in the log here. Let's see. Yeah, it was asking for 1.924, and it was set to not exceed 1.44. So I just went in there and said, well, you can ask up to 50 and you're fine. I'll probably take that out, or at least drop it down from 50 to 2 millimeters per, well, this is just square millimeters. It's basically the nozzle diameter times 4, I think. I don't remember what the 1.44 comes from, but it's something like that. And it's just trying to control the amount of filament requested to exit the nozzle on a cross section. Basically the kind of the line width that you're trying to do, and it's trying to control so that you don't have gaps in the model that you're printing. And the G-code generator that we looked at just a second ago was requesting more than that, and so I did have to override the default setting, and so I just set it to 50. So if you're running Clipper and you get this error, then go into your printer config and add a line like this. 50 is way overkill, but add that line at least for the flow test, and then if you complete the flow test and you're fine, everything looks okay, then just comment that thing out and save it and restart if you don't want to run the risk of asking for so much filament that it gives you gaps in your model. So then we printed. It took 7.5 minutes to print. So the 7.5 minutes was to print all of these and their purge lines that are left on there. And then what you would do is you would take and you would weigh each one of them, except my scale can't measure low enough resolution for these tiny ones. 100 millimeters of filament may not be enough to get a good sense for this. You might need more filament coming out. I don't know, but you would plot this in Excel, and well, we can look at that. There's some, these aren't my plots, but where did I put? I guess it's in here. So, oh well, let's see. Let's go to here. It's on this first link here. So he's got them way more densely packed than I have. So you can plot something like this. And you should, at some point, assuming you ask for too much flow out of your nozzle, then you should see some corner where it drops off and it's just not delivering enough filament. So this is just a regular Ender, what's an Ender 3 Pro, and what's plotted here is, well, he's plotted the amount of under extrusion, so basically the percentage weight of the little blobs as what their theoretical should be. You could just plot the weight of the blobs and it would give you a similar plot. It just wouldn't tell you how much under extrusion percentage you're getting, but you could just plot the weight of them and they'd look the same. So it looks like right here for this particular printer at this is 200 degrees Celsius, so it's the gray line, at 6 millimeters cubed per second. So if you're ever requesting more than 6 millimeters cubed per second, it's really going to start to struggle and you're going to have gaps in your model. And you might even have gaps at 6. 4 is way safer. 6 looks like you're 5% under extruded, which is probably okay. Well, in my Cura settings, you saw I was set my flow rate to 5% of maximum anyway. I think he's got some other, well, that just describes all of the settings that I just described. That's the same. Here's multiple plots. So same printer, same test, but 3 different temperatures. And so you can see as you go up in temperature, which makes sense, you can flow more filament out because it's melting faster. You might have other problems, like your surface finish might degrade. So you have to balance. This test does not look at surface finish at all. It's just printing blobs. The nozzle just sits there and kind of gradually goes up and spits out filament. So you can't really get any information from that as far as surface finish goes. But you can see here now you might be okay up to 10 cubic millimeters per second. So you could take that number, put it, if you're using Prusa Slicer, you could put it in as your maximum flow rate at that temperature. So if you're printing at 240, which is kind of hot for PLA, then you could set your maximum flow rate at 10, and it would modify the speeds that you're asking it to print to where it never tried to deliver more than 10 cubic millimeters per second of material. Or if you're using Cura, then you could go to the flow graph and make sure that the maximum is less than 10. If you're nowhere near 10, then you could ask for a higher print speed. Now you might have other issues. It might not be that you would get a nice print just because your flow rate is higher. You might have, artifacts from the motion, the kinematics itself, the thing moving around. You might have artifacts, vibrations, ghosting, that kind of thing in the print at the higher speeds, but you wouldn't have flow rate problems. So that's a thing you could look at for relatively easily, assuming you have a way to measure fractions of grams. Even with the more filament, the double the filament, I think I would still need to be able to measure fractions of grams in order to get something usable out of it. You can at least get your maximums, because you can hear the printer skipping when it's trying to deliver more. You can hear it popping when it's printing too fast and too slow. So you can get those maximums just from listening to it. Looks like here he did actually plot the flow rate itself. There's some examples of under extrusion. He goes on, I think he's looking at different layer heights there. Let's see, I did also I linked this one paper. Let's see, I think it's this one. Yeah, I linked it because it had the paper is about graphene enhanced PLA. So PLA with graphene platelets in it. And so it's not any filament that you can even buy, I don't think. I think there are graphene filaments. I think this is a filament this research group actually made for testing out surface finish by adding graphene. A lot of times you add graphene, it's to make it conductive, actually. I don't know if that's what they were doing here or not, but they had this picture. So these are different flow rates. They also change different line widths. And you can kind of get an idea of over extrusion is all this lumpy stuff. Under extrusion is a little harder to tell, but this 70% over here, and even the 80% you might can tell better, where the lines aren't touching each other when they're trying to fill out the top surface. You can kind of see that's under extrusion. Now their 100% is not nice though, so they definitely still have issues over here. But there are people out there who are trying to let's see who these people are. Trying to determine, what are some of these parameters. Flow rate is one that doesn't get in a lot of testing done on it generally. There are a lot of printing settings that you can change. Flow rate's not one that gets a lot of look. Temperature certainly gets looked at a lot, but flow rate doesn't necessarily get researched a lot. So this is one of the few papers. This is relatively recently, I think. Let's see if we can find their 2022. Yeah, so published a year and a few months ago, or a month ago. So what they're doing here is trying to do a kind of like what we did here, or what I did here, but with different line widths and different flow rates. Oh, it reminded me of one thing I was going to tell y'all before. Sometimes you see this term, fused filament fabrication, FFF, and sometimes you see FDM. I don't know if they used FDM in this paper. There's a reason why a lot of times, particularly in like journal articles or online or something, you will see the FFF more often. And it has to do with a trademark. I went over to the uspto.gov. Do I still? Yes, here it is. uspto.gov is U.S. Patent and Trademark Office. So if you look, this is a total aside. It doesn't have anything to do with flow rate. If you look at trademarks and search for trademarks, we'll just use the basic one, and search for FDM. You get a bunch of them. So the way trademarks work, again, this has nothing to do with printing. Well, it's kind of printing because it's FDM, but nothing really to do with flow rate. But the way trademarks work is there are hundreds of categories of products and services that the trademark could exist in. And so that's why you see a bunch of these different FDMs. They don't overlap. One of them, well, here's one for cabinet making, and there's going to be one in here for 3D printing, and there's going to be another one in here who's just the initials of some company somewhere. There's a bunch of dead ones. So that doesn't necessarily mean the person that owned the trademark is dead. It just means that that trademark is not actively being used. So if you wanted to, you could go use whatever this one is. It was abandoned. So it's just this little type. It was by Simple Technology. So maybe that company went out of business, or they don't use this trademark anymore. They didn't pay some kind of renewal fee, and they didn't use it, and it was abandoned in 2002. So they used it for 2 years maybe, and then abandoned it. But one of these, I think it's this one. Let's see. Is that? Yes, this one. So this one has to do design of objects for 3D printing. This one's actually for the software, but it's owned by Stratasys. And so Stratasys is one of the bigger companies in 3D printing. Most of the stuff they do is more on the industrial side of printing. But MakerBot is also part of them now. I think they bought MakerBot. And so I don't know what MakerBot is doing these days, but that's why you'll see FFF instead of FDM, meaning the exact same thing. Is you'll see they didn't want to even have an issue with using a trademark term here. Sometimes you'll see FDM and the little TM trademark, or the circle R for registered trademark. And then you could say that, hey, this isn't our trademark, this belongs to somebody else. But a lot of times if you're worried about it, you just use FFF to mean the exact same thing as fused deposition method or modeling, and it's fused filament fabrication, which I actually like better anyway. But that's why you'll see that. All right. But this paper, I mainly got it to show you this, but then you know how papers, they give you a bunch of references, right? Somewhere. Here they are. I grabbed a couple of other papers from this paper. So we don't need a trademark. Let's see this one. So here's one. This one is, I don't see the date, 2017, so relatively new. But it's tensile strength for FFF, 3D printing. Again, there's the FFF. And so they are using the ASTM standard here. So that's basically, I doubt I can find that. Let's see. But it's basically the setup for, yeah, how to make and run a tensile test specimen. This one's specifically for additive. Oh, this is a terminology. Yeah, so that was just a terminology. They actually used the specification. I don't know which one they used. Probably D638. I just don't see it. Because that's the normal one that you use for tensile test specimens, plastic ones. But they went here, and they weren't necessarily directly trying to find flow rate. Okay, there's the standard right there. This one is more about determining if you have printed a part, what are the ways that you can determine if it printed well. So that's related to flow rate. Mainly they're thinking of flow rate on the infill. So that was kind of interesting, but I didn't read much of it. This one's more interesting because sometimes you intentionally modify flow rate. So here, this paper, let's go to the top of it. So this group, they intentionally reduced flow rate to create kind of a fabric material. I remember seeing this maybe on YouTube somewhere, where you get, with a reduced flow rate, you get this pulsing blob effect, and it creates a fabric-like material, and you're intentionally reducing the flow rate to try and create more of a textile type of material. So that was interesting, for a reason to actually, here's like fold it up to make an entire skirt. There's making a birdie for badminton. And this one you can kind of see the obvious under extrusion, but that's on purpose in this case. So there are some reasons when you might intentionally want to modify the flow rate. I don't remember. Here are some of the different patterns where change in print speeds and extrusion. So the extrusion multiplier is the same thing as flow rate 95% or whatever in Cura, but other slicers call it extrusion multiplier. I think Prusa slicer calls it extrusion multiplier. And so they went down all the way down to 30%. Now these actually, it looks like they're using simplified 3D because their print speed is millimeters per minute. So that's why it's at 12,000. That's not per second. And so you can kind of see these interesting patterns that they're getting by intentionally reducing the flow rate and printing at faster and faster speeds. So I thought that was neat. Then I saw this paper. I have not read it yet though, but it is a real-time monitoring system. So it looks like they are using a camera to watch the print as it's happening. And there's been one of these that's the spaghetti, I don't remember what it's called, but spaghetti monitor. We'll look it up in a second, but it would just have your webcam, watch your printer, and then you would be connected to a cloud service that would be processing the images from your webcam. And if it ever noticed spaghetti, so like your print came loose from the bed or whatever, you know, it's not printing right, it would send you an alert that, hey, something's wrong. This one is, I think, way more sophisticated than that. I think they're actually trying to get actual quality, not just that it's failing, but that it can modify mainly the extrusion multiplier here. So it's looking for over extrusion or under extrusion, and if it lands on either of those, then it will go in and change. You know, you can tune these settings as you print. On your printer, you can go to the little panel, or if you're using Clipper, you can go to the Clipper interface and tune flow rate, temperature, speed, print speed. There's several things you can tune during the print, and so it's taking advantage of that and feeding back and hoping that it improves the print quality. So with these little lines here, it makes me think it's a neural net that's doing that. And they probably have a camera that's looking right on the nozzle. There are nozzle cameras. I haven't ever used one, but well, it looks kind of like they might have a webcam, USB webcam mounted like right there, looking at the print that's happening. I think that's kind of what they've got going on there. There are better solutions than that now. I don't know how old this paper is. Let's see. 2019. It's not very old. But there are nozzle cameras that you could probably just get pretty cheap and get a better image of what's going on with your print. Although they might have needed the longer field of view here for their processing to make sense. Maybe that's why they did this. Looks a little weird with the camera there, though. So I found those. And then I, back on the flow rate, I was like, well, I did order a scale that will be able to measure tenths of grams so that we can actually get a better idea of what's going to happen with our flow rate. But I thought, well, what I've got in the printer right now is a 0.6 millimeter hardened steel. So I think I could probably get better flow rate with a different nozzle. So I could just make it bigger, 0.8 millimeter, 1 millimeter. That's not really the route I want to go because I do want to be able to print, you know, down to 0.2 millimeter layer heights, and I don't want the walls to be too thick on a lot of these prints. So there are different nozzles that you can get that increase flow rate. So here's one of them. This is the Bondtech CHT. The MK8 is just the basic shape of the nozzle, but the 0.6 millimeter. So, and they have a 0.4 and a 0.8 also. Now this is $20 plus shipping for one. It shows 3 in here. It's just one. It is a brass nozzle, even though it looks silver. So you can't run abrasive stuff through it because it is going to be, at its core, it's just brass. It's just plated with nickel. But you can kind of see over in this left-hand picture what's going on with it. It takes your filament coming in. Your filament's already soft at this point because it's right above the nozzle. And it splits it into 3 tracks. So basically your 1.75 millimeter filament gets split off into 3 little pieces, smaller than 1.75 millimeter diameter, so that you can melt those individual strands faster than you can melt the core of the solid filament. And they do work. This one, you know, it's $20 plus shipping. I don't know how long it takes to ship from, this is Matter Hackers. So it's gonna cost you $30 to get one of these. I ordered these. So these are clearly not the same. I ordered it just this morning. This is a pack of 5 for $12, including shipping. So way cheaper. They are not the same. For one, you can kind of see their little splitter is a separate piece. And just based on the colors here, it looks like the nozzle is regular brass and the splitter is probably copper. Is what it looks like. It does not look nearly as sharp. You know, it doesn't look like it's going to do as good of a job slicing up the filament. But it also doesn't, I can't tell, you know, I don't think they give you a cross section of what that thing looks like. But I think it's just an insert at the top. I don't think it goes all the way through the thing like the Bondtech. Bondtech's certainly better, but way more expensive. So we're going to try one of these. I got the 0.6. So same diameter nozzle, but it does have a split in it. So I don't know when they'll get here. I expect they'll be here soon. And we'll see if, first of all, if we can get decent prints out of this thing, or if it just clogs up all the time. But we'll see where does I've just got a regular 0.6 stainless steel. The steel is not going to have as good of a heat conduction as the copper and brass are going to have. So it's going to suffer there, but we'll see if I'm not printing abrasive material, just plain material, then do I get a higher flow rate from something like this type of nozzle? If I can find, I have some of these, I just don't know what printer I put them on. So if I can find one of these, then I will put one of the Bondtech CHTs in there also. I just don't want to buy another one right now. But if I can find one that I have already, then we'll test one of these guys out too. And see how well, if there's any difference at all, and if it's a positive difference or not between this guy and what I've already got in there. So this one does have the advantage of being copper and brass, so it's going to have better heat transfer. I don't know that this is going to do a super great job. I might have to go in there and like file the little edges to make more of a sharp split, but I don't know. We'll give it the filament's going to be soft at that point anyway, so it should flow around there without too much trouble. But I don't know if this will be just more of an obstruction to flow rate than what the Bondtech has with its much sharper edges. So we'll see if it makes any difference at all. All right, let's see. Do I have any other tabs open here that I wanted to tell you about? That's just the clipper. I was originally planning on doing today. I was planning on doing the photogrammetry, but I just didn't get it set up. So I think that'll probably be Friday. Class 24 will probably be the photogrammetry. I don't think I'll have time to do it for Wednesday. I have to go set up and take pictures. I think what we're going to do with it, though, is we did the form hood scoop in Fusion 360 based on a LiDAR scan from an iPad. That was last week. And we did that, but I can't print it very easily because it's a big thing. So I thought maybe we might do air vents, like fake air vents for the engine compartment that you would see on the side of a fender, and we'll use photogrammetry to capture the fender geometry, which is pretty normal anyway. It's nothing fancy on that truck. But we could print something that size because that's within the size of any of these printers. So that's what I'm planning to do, is do photogrammetry to get the side profile of the truck fender, and then we'll just do a little engine compartment air vent, probably a fake one. I don't think I want to actually cut a hole in the fender for that, but one that you would just stick on there, and we'll model that in Fusion 360 similar to the way we model the hood scoop. I don't know if I'll do all of that on live stream or not. I don't know if y'all are even interested in the Fusion 360 form modeling type of thing. But we'll model it up and print it out. We also, probably what I'll start Wednesday is assembling the Rook 2020. I don't think I'll assemble it on the stream just because that's kind of boring to watch. It's not very educational unless you're building one also. So we'll look at that. Oh, I did I made this. So went and got Dr. Pepper bottle. This is what's left of it. This plus the bottom, the very bottom of it. And I made this much PETG. I haven't printed any of it, but it doesn't make a lot. Got kind of tangly there. But it does look like it's pretty well shaped. It's a little oversized. It was 1.8-ish millimeter diameter instead of 1.75 millimeter diameter, so it's a little oversized. Hopefully it's not so oversized that it doesn't feed through the hot end, but we'll try actually I'm going to try dyeing this. I have that teal blue color RIT synthetic dye. I'll try dyeing this, and then we'll try printing. I don't know that this is enough to print a vase. It might be one of these vases, but if it is, we'll try and print what we can. But that's how much you get. It was relatively straightforward. The only downside is the stepper motor that's being used to drive the take-up reel on the Recreator 3D is just a little underpowered. There's two ways we can take that and maybe fix it. One of them I actually might try showing you. I don't know if I can easily get to it on the printer or not. We'll see. But there's a reference voltage, and I actually think this printer, but this one might be the one I try to show you on. I think the reference voltage is too high for the stepper motor back there for the y-axis because it gets super hot, just normal printing. And it shouldn't get that hot. So I think it's running too much current through it. And I don't want to burn up the windings too early or anything. But I think on the Recreator 3D, it's running too low current. The motor's not getting hot at all, but it's just a little too underpowered to pull the filament. I had to help it occasionally. It would either skip or release its holding torque entirely and unwind. So one way I could fix that potentially is changing the reference voltage. I don't really do that very often, but I think on this printer I actually need to, because I think the reference voltage for the y-axis is too high. So we'll go in there and I'll show you how to do it. I don't recommend doing it unless you really know what you're doing, but I think this printer needs it. And then the Recreator might need it to bump up. The other thing we could do is get a higher torque motor and put it in there. I didn't find any though. 24 volt higher torque NEMA 17 style motors. So maybe we'll try adjusting the current on that. So that's kind of the coming up plan. We'll look at reference voltage adjustments. That's not going to take very long. Hopefully we don't burn up anything. And then I'll look at whatever progress I've made on assembling the Rook 2020. I think I have all of the pieces for it, other than a heated bed. I'm not going to run a heated bed anyway, but I don't have a bed at all right now. So I'll have to figure that out. But we'll be back Wednesday with those things. Friday with the photogrammetry, and maybe a little bit of